Um, Welcome back for the afternoon session. We'll start off with the talk by Andrew Myers on synthesizing protocols for information flow policies.
Okay, so this talk has a strong relation to some of the previous talks we heard this morning, which were really interesting, in that it's about trying to make it easier to build secure computations with higher level languages, or higher level languages that then allow us to synthesize computation. And this is actually a problem that I have been thinking about for a long time, and even maybe making a little progress on it. And kind of picked it up in the last couple of years again, I think largely due to Elaine Shih showing up and pushing me to work on this. So here's the high level goal is kind of similar to what we've seen in some previous talks. I think Manuel had a picture like this too. We'd like to be able to write source code at a high level, maybe stick some kind of security policies into it, and then we'd like to send it into a magical compiler that can compile our code so that it runs on whatever devices we have sitting around, whether it's your local handheld device, maybe some trusted hardware that's sitting somewhere, running on the blockchain, servers on the cloud, wherever is appropriate. And it should automatically deploy various security mechanisms for us which otherwise we're probably going to screw up if we try to write the code ourselves. So crypto protocols, trusted hardware, distributed protocols are the kinds of things that Elaine talked about. These are all things that are notoriously difficult to get right. And modern applications are trying to use multiple of them at the same time. And the Venn diagram that somebody showed earlier has even more bubbles failing to intersect these days. Okay, so this, so what's my secret sauce to solving this problem? Well, this view of things connects nicely, in my opinion, to the idea of enforcing information flow at the language level. So I'm a programming languages person, not a cryptographer. Don't beat me up too hard. So the goal here is that we want to write code, and the code is going to be annotated with policies that talk about confidentiality and integrity. So confidentiality means secrecy, integrity is about how trustworthy our information is. And we're going to write our source code. It will have these policies that talk explicitly about the trustworthiness and secrecy of the data the program is manipulating. And then we can have a compiler look at this code, and it can check whether the code obeys the information flow policies. Does information flow from more secret locations to less secret locations? Or does it flow from less trusted locations to more trusted locations? And the compiler can say, yes or no. Okay, so that's the goal. Now, the neat thing that we observed in some work that we did actually a long time ago now was that you can actually use these information flow policies to drive some of the synthesis of distributed systems that implement these things. Actually, I was really tickled a few weeks ago to discover there's a DARPA program based on these papers. So maybe more people will be reading these papers in the future. Anyway, so the idea is then we'll have that same front-end compiler that checks that the information flow in your programs satisfies the rules for secure information flow. And we have a special back-end which is going to rip apart that code so that it can run securely on a distributed system. And in the process, it's going to have to invent a protocol for these things to talk to each other. And that protocol involves some cryptography in the work that we did, although fairly limited cryptography. So this is actually not just going to be a talk about very old work that I did, but it's actually mostly a work in progress talk. So I'll get to the work in progress, but let me give a little background in the context of the older work. So the idea then is we're going to have these information flow policies, talking about confidentiality and integrity. And the policies are what we call labels. The labels are actually part of the types of things. You don't just say that something's an int, but you say it's an int and it's secret, or it's Alice's int. So the policies are expressed, these labels are expressed in terms of principles. So we'll assume that there's some set of principles that are kind of atomic entities. And if we can actually use a label, we can use a principle as a label for information. And what it means to label something with a principal A is that that information is both trusted by principal A and secret to principal A. So that's a pretty restrictive policy on the use of that information. And then we get more expressiveness by introducing some operations over labels. So there are two key things we can do. One is we can project a principle or a label in general to only be about the confidentiality aspects of that principle. And we can also project onto only the integrity aspects of the principle. So A right arrow means this is information that is secret to A. In some sense, A thinks that it's only going to go to A. And A left arrow means that it's trusted by A. A thinks that A, in some sense, is the only influence on this data. Now we can also, so you can already see that we're now able to talk about different aspects of security just by these right and left arrow projections. We can also combine principles. We can talk about A and B, which means a principal who is at least as trusted as both A and B. And that means that, and interpreted as a label, that means that this is information that's trusted by both A and B, and it's secret to both of them simultaneously. So basically, either one of them can only see it with the agreement of the other one. And that's distinct from the information flow meet, which is that upside down intersection operator. That is information that is allowed to flow to both A and B. It's trusted by both of them, but both of them can see it. Okay, and there's a couple more operators, which you can imagine the usual duals. Yeah,
so in the previous slide, you mentioned like flow and synthesis. And again, I'm not a PL expert, so I apologize if my question doesn't make sense. But when it comes to flow, I imagine it's about verifying if something doesn't do something bad, versus synthesis is like, I have something that is confidential, like I shouldn't reveal it, but I can still do possibly some secure computation with it, which means I want to synthesize code to maintain the confidentiality. I don't know if I'm...
Yes. I mean, I think the idea here is that there are going to be some computations that you want to run on your distributed system. And given the amount of trust that you have in the various machines, devices, whatever, that are running the computation, you might need to use some kind of security mechanism to achieve the security goals. So to keep the information confidential.
My question is probably, you have a sort of
basically, in a crypto language, like let's say you want to write a gigantic ideal functionality that expresses the whole thing, and everything is in this gigantic ideal functionality. The synthesis takes this gigantic program and breaks it apart into like F commitments and FMPC and F0 knowledge proof, and makes sure like these F commitment, FMPC, like they're not called, well, whenever they can be avoided, we don't want to call them. The information flow makes sure that you don't write a bad ideal functionality. Like let's say the ideal functionality itself has a internally consistent policy. Like you didn't accidentally say, this is secret to Muthu, but later you declare, oh, this is not secret to Muthu or something like that.
Yeah. Okay. We'll get there. Okay. Yeah. So I agree with everything Elaine said. So the key thing is here that the information flow from between different labels then has to be secure, and there's a square less than or equal operator that captures when that is true. And I won't get into the details of it. And the other point is that these various operators can be combined, so we can talk about the integrity of A and B simultaneously, and there are various nice algebraic identities that you can employ, and all I think are pretty intuitive. So then this space of labels forms a lattice, and ordered by that square less than or equal operator, and the compiler is going to check that all the information flow in the program is secure in the sense that it goes in the direction of the lattice. And one of the things that's interesting about this lattice is that you can see there are actually kind of two axes here. There's a direction of secure information flow, which is in the direction of decreasing integrity and increasing confidentiality. And there's a direction of increasing trust, which is where confidentiality and integrity both increase. In some sense, it's the fact that those two axes are orthogonal to each other that makes security hard. Okay, so now let me show you how we can actually use this to synthesize an interesting implementation. So my standard example for this is the game of Battleship. So you guys have all played the game of Battleship probably, right? So you have two people who have a board. They get to drop bombs on each other's squares. One of them says C3, the other one says star, and it's a hit. And at the end of the game, then both people show their boards to each other and prove that, yes, actually, my board was what I said it was. And I didn't secretly stick all my ships off to the side. Okay, so now imagine running this game on a distributed system where Alice and Bob don't actually share a computer and they don't trust each other's computers. Well, then there are a lot of concerns here. So for example, Bob might, whenever Alice says C3, say, oh, well, I'm just going to move my ship over a little bit and declare that that was actually a miss, right? And then at the end of the game, Bob can still show that the board is she just kept missing. Too bad. Okay, so what that tells us is we have confidentiality and integrity concerns here. So thinking about Alice's board, Alice wants it to be confidential so that Bob can't just drop bombs. And Alice and Bob both need to believe in the integrity of Alice's board and in the integrity of Bob's board, so that neither one of them is able to modify their board once the game starts. Okay, so now if you imagine running this program on the distributed system I described, it sounds, on the face of it, problematic, right? So the label on Alice's board says that it has to have the full trust of Alice and the integrity of Bob. And so if we put it on Alice's computer, then that's going to violate Bob's integrity. And if we put it on Bob's computer, that violates Alice's confidentiality. So this is a place where we seem to need a trusted third party, or we need some fancy cryptography, or maybe some not so fancy cryptography. So what we're going to do is use cryptography to implement the trusted third party in this case, in some sense. So the solution is not too surprising. We want to take that board and replicate it onto both of the hosts, and the host that's not allowed to see the actual information and is just asking for integrity gets a bunch of commitments for the contents of the cells of the board. And then on Alice's version, Alice has the clear text, but the clear text is also paired up with nonces so that Alice can then open the commitments, and Bob can check that, yes, Alice is not cheating every time that Bob drops a bomb on Alice's board. Okay, so the neat thing about this is that in our compiler, so GIF is a language based on Java that has information flow in it. We built this special version of GIF with a partitioning backend that I described called GIF split. And the GIF split compiler lets you write a GIF program that says, well, there's just this one array variable and it has it has Alice's board. But what the compiler actually does is say, oh, given that I have to compile onto Alice's computer and Bob's computer, I don't know how to do that without doing a transformation where I replicate the board and create this hash replica and I synthesize these commitment protocols. So the compiler does all of that stuff for you. If you look at the source code, you don't see any cryptography at all. You don't see any replication, even though there's replicated computation and replicated data. Okay, so that's the idea. And one thing that's interesting about this is that is the role of downgrading in this system. So downgrading is something you have to do to use information flow controls in practice. People would like, a lot of the theoretical work on information flow is done in a setting where you don't have any downgrading and you're sort of proving that you have no information leakage whatsoever, but real systems have to leak information, often just as part of their intended functioning. Like, for example, in the Battleship game, Alice's board is initially confidential to Alice, but at the end of the game, she needs to show it to Bob. So clearly, something changes. So that's so there are various ways to capture that. You can have even more fancy information flow policies that talk about that thing coming up and kind of couple it with some sort of temporal logic. But downgrading is the typical way that this is done. So we have declassification, which lets us relax the confidentiality side of the policies, and integrity that allows us to relax the, endorsement that allows us to relax the integrity side of the policies. So what endorsement means is you have something that's untrusted, but you'd suddenly treat it as trusted, just because for reasons that are kind of outside the scope of what the information flow stuff can do. So for example, when Alice makes a move and sends it to Bob, it's part of the game that Alice gets to do that. And so Bob endorses that and says, okay, I'm now going to consider that to be Alice's move for this turn of the game. So that endorsement then actually causes the system to do something interesting. So at the type level, at the source language level, these declassify endorsement things just look like typecasts, right? So you normally think of a typecast in a language like C as kind of having no real computational content. It's just, please pretend the following thing. But when we're thinking about the distributed system, these typecasts actually often come with a whole bunch of interesting things going on. They're actually places where we're doing some cryptography. So the endorsement that happens when I send moves over, actually not the moves, but the board cell locations to the other side, that's going to correspond to creating a commitment. And the declassification that happens when I send the contents of my cell back to somebody who tried to drop a bomb on it, that's going to be opening the commitment. So these downgrading operations, declassification and endorsement, they're actually interesting, and we're actually synthesizing code for them. Okay, so I just described to you how we can synthesize commitment protocols, and I didn't give you the details, but they really come out of this table here. So here what we're saying is, if you look at the different possible combinations of confidentiality and integrity policies, then they suggest different cryptographic mechanisms that we could use to achieve them. So in many of the cells here, we don't really have to use any cryptography because there's enough trust around to simply place information at a node. And what we would like to do is have the compiler use those cells whenever possible, because that's really efficient. But then there are some places where you can't. So like the upper, the top center cell is the cell that we were in the battleship example. And there we're sticking a hash replica at one node. Now it turns out we don't have to do any fancy computation on that hash replica. But in general, if we want to do computation involving it, we're going to need zero knowledge proofs. So we've sort of explored a part of that upper cell. The whole horizontal, the middle row there, the A and B right arrow row, it corresponds to something where we want the power of MPC or some other protocol that has the right properties. And that is something that we haven't explored, but clearly from the talks this morning, people are moving in that direction. And it is something we are exploring now, I should say. So the other thing I want to point out is that I commented that the top center cell there, in general involves zero knowledge or some other mechanism, but if you have a particular kind of computation on it, you don't have to use that, the computation in the battleship example. So in general, what computation you're actually doing over data in one of these cells might govern what kinds of crypto protocols you can use. And ideally, you'd like to choose the cheapest protocol or mechanism that you can. Okay, so here's another example. So this is a famous game that people get cheated at, but this is a totally trustworthy version of it. So if you remember the way the shell game works, there are two players, we'll call them Alice and Chuck, and Chuck places a P under one of three shells and then shuffles them around. And Alice wants to know that somewhere under those shells there is a P, and then she gets to guess one of them, and Chuck reveals that, oh, sorry, you lost money again, or optimistically that she found it. Okay, so if you think about the security policies of this game, we can actually express them with the kinds of labels I've been talking about. So for example, Alice knows that Chuck has placed the P under one of the three shells. What that says is the information is trusted by Chuck, right? Otherwise, Alice might move the P herself. And it's also secret to Chuck, of course, because Alice shouldn't know ahead of time. But Alice needs to believe that there actually is a P in there. So Alice's integrity is needed, okay? And if you think about the outcome of the game, well, the outcome of the game is something that both Alice and Chuck can see. So that can flow to the disjunction of the Alice and Chuck principles. But they both need to believe that the outcome was computed correctly. So it needs the conjunction of their integrity policies. And so that's where we use that lattice meet. Okay? So then, given those policies, we can write this code here. And this captures the core computation of this game. Okay, and I won't walk through the details of this, But here is an example of how we could compile this protocol, this program, using MPC and zero-knowledge proofs and hashes and so forth. So various mechanisms are getting used. Okay, so this kind of represents our state of the art. We don't actually have a compiler that can do this yet. This is hand compiled laboriously, and so the place where we are right now is we're trying to build the compiler that can do this. Okay, so Elaine commented earlier about the connection between this and ideal functionalities. I wanted to say a few things about this, the way that I see it. So ideal functionalities are a nice way of capturing a security policy by talking about what influences and what knowledge are allowed in the system. And in the information flow setting, we use these labels to capture it. So I think a natural question is, well, what's the relationship between these things? So the information flow view of this, when applied to a distributed system, says, well, if you have a low integrity label, what that really means is that the adversary, so low is kind of defined relative to the adversary we're thinking about here, but the adversary is allowed to kind of come in and stomp on that data whenever they feel like it. That's what it means to be low integrity. And to be low confidentiality, it means that that information keeps getting leaked to the adversary at every step of the program. Okay? And another way to think about this is that in some sense, every label in your program, in your labeled program, is kind of like a virtual node that, kind of a virtual principal that's out there, and you can kind of view the program as a whole bunch of these things, as many as you need from your lattice that are communicating with each other. So then the way that I like to think about this is that when you write down your program, like the program in the upper left, and you think about it with respect to some adversary. So in this case, I'm thinking about the adversary being actually the player Alice. And in the information flow setting, we really want to be secure against all possible adversaries. So then we can imagine that there's a little attacker program, which is the program which reads from all of the variables that Alice is allowed to read directly according to the information flow policies, and writes to all the variables that Alice is allowed to modify. And that program is interposed basically at every program point. And that, in some sense, gives you the corresponding ideal functionality for the program. Okay, but I think there's something nice about the information flow view, and that is that in the ideal functionality world, in some sense, what you're saying is, what security do you get? Well, you get whatever the ideal functionality says. You're kind of saying the spec for this code is the code. And from a kind of software engineering methodology standpoint, this is not a good position to be in, right? And maybe it works fine when you're thinking about really small things, which of course most of us want to think about when we're doing crypto, because it's hard to think about big things. But when you scale it up, you're never going to be able to live that way. So we need something that checks that these functionalities that we're writing down are actually sensible. And so the nice thing about that is that when you write down these information flow labels, it immediately starts constraining what can happen in the code. And what we found repeatedly is that when we write down programs using information flow labels, we start discovering things we didn't think of. And it gives you a lot of insight into what's going on from a security perspective. Now, in general, and almost always, you end up sticking in downgrading at various points in the program. And every time you stick in downgrading, it's a question of, it's a chance for you to think, okay, is that really a sensible thing? Why is downgrading okay here? And you have a little, argument with your office mates about this. And that's a really, really constructive process, is what we found. Okay, so this is why I feel that this information flow view is, in a sense, more declarative than the ideal functionality view, where you're kind of getting a more emergent version of security. Okay. All right. So one other thing I wanted to mention is that downgrading itself is, of course, a bit problematic. And if you're not careful with unconstrained downgrading, you can get yourself into a lot of trouble. So there are actually some additional checks, which I don't have time to go into detail about, that are there to make sure that you don't use downgrading in a way that opens you up to vulnerabilities. So for example, we have a property we call robust declassification, which says if you're declassifying information, then you don't want the adversary to have control over that declassification. This is sort of intuitive. But so it's actually connecting the integrity and the confidentiality axes of that lattice that I drew before. And so our compiler then statically checks that you don't have that improper influence of integrity on confidentiality. And something we've discovered pretty recently is actually there's a dual to that, which we call transparent endorsement, which is you don't want high confidentiality information to affect endorsements that you do. And we have some examples in our recent paper about that. So putting these two things together, we have a property that we called non-malleable information flow. And I apologize for the name non-malleable. It probably bothers people here. We couldn't think of a better name. And it seems to be connected to malleability. So, so that's what we call it. And for those who know about hyperproperties, it's a force safety hyperproperty, which is kind of a cool thing because nobody had really previously identified a kind of naturally interesting hyperproperty above 2 safety. Okay, one other nice thing about information flow is that we can actually talk about timing channels in a nice way. So somebody earlier mentioned that, what do you do about timing channels? And the cool thing about it is we can actually use information flow reasoning about timing channels if we have an appropriate contract between the layers of the system. So the insight here is we don't actually have to require that computation time is constant. Right? That's the standard way that people try to do things in the crypto world. But all we really need is that computation time doesn't leak information to people who shouldn't see that information. Okay? And in fact, when people try to implement constant time computation right now, they're not really necessarily getting it because there's no guarantee from the hardware. The spec of the hardware doesn't say that it's constant time. So I think the real solution to this problem is that we need specs that actually talk about information flow. The hardware needs to give information flow guarantees. And in fact, what we've been able to show is that we can express a kind of software-hardware contract using labels that talk about timing. And we can then build hardware that enforces that contract. And the way we do that is by sticking the same kinds of information flow labels that I've been talking about into the hardware description language. So we have Verilog with labels stuck into it, and then anything you build in that hardware will not have timing channels. Okay, modulo the usual downgrading issues. Okay, so in conclusion, I think this is an interesting direction, I think we definitely need to have higher level languages for expressing these kinds of computations, and I think a lot of the folks in this room are thinking about that kind of problem, and I look forward to having more conversations with all of you about it. Okay, thanks. I got the coveted after lunch slot. Sliding into slumber. Okay. Allie?
So when you're talking about, so I agree that information flow policies could be a good way of convincing yourself that an ideal functionality is well crafted. But the thing I don't think that you talked about when you told the story was the connection between the ideal functionality and the simulator. And at least, I mean, you may be thinking that in your head, but in terms of trying to communicate with this community, the crypto community, you probably want to make that explicit. And so the thing is, right, that the ideal functionality has kind of external behavior that is in line with the real functionality, but
right.
But it's limiting, circumscribing what the simulator has access to when it tries to simulate for the adversary the rest of the observable behavior. And so I just was curious, why didn't you talk about that?
Right, so I didn't want to talk about this a lot because I would probably make a fool of myself if I tried to talk too much about UC. But we actually are collaborating with one of Greg Morisset's students, and I think Greg Morisset himself, on building an underpinning that lets us prove formal things about this by translating down to the UC framework. Okay. Yes, probably.
The paper, the language in Ron's paper to write your ideal functionality. So we also want.
Okay. All right. Thanks for the feedback.
To that, to what Ali's saying. So we could think of, there's an interface sort of between the ideal and the simulator, right? And those types that Andrew's talking about are expressing that interface.
Yeah, I think that's right. My hope would be that in some sense the simulator could be extracted from the types, the things that are the external interfaces to the program.
The capacity of the simulator, right? Like what it's able to do can be
Yes.
extracted from those types, because the interface constrains what the simulator is able to do.
Definitely the way they, no, I never thought that anybody would actually write minimal ideal functionalities in Turing machines, and definitely having higher level programming languages that allow you to write ideal functionalities and also protocols in a more structured and meaningful and in a way that you actually can see what's going on would be great. And improving properties on ideal functionalities is also great. And it's like, obviously, that's the way to go.
Thank you.